Hello everyone, my name is Sanjeev Kumar Khan and I am a senior research scientist in Siemens Healthineers. Today I am going to share our work on multi-step radiology report summarization. Basically, it's an innovative approach to uh, take a radiology report, especially finding and generate the impression part of that report using these summarization algorithms. And we have some innovative component in this summarization approach of taking the findings and generating the impression. So basically, the idea is to support radiologists to quickly go through several report and generate the impression sentences, and radiologists just look at those impressions and also have those explainability, how those impressions were compiled by the model, and then eventually, if necessary, make the edit, or if everything looks good, they just channel it back to the referring physician so that the referring physician does the necessary diagnosis of the patient. Um, so following is the table of content for this presentation. Let me jump into introduction. So as you can see on the right part, you see a sample of radiology report, and this report has a finding section which basically describes normal and abnormal imaging results that the study that the radiologist performed. And then on bottom you see impression section where the radiologist basically make a conclusion out of the findings. And this impression is basically the important or the core diagnoses that were found during the study in the finding, and this eventually will be consumed by the referring physician. As several study or survey have shown that 43% of referring clinician or physician only read impression if the number of findings goes beyond the page. So it is very necessary that a radiologist write this very precise impression such that the referring physician makes the right diagnosis for the patient. And also this impression that the radiologist eventually, if manages to uh, get through a model or a system, needs to have some explainability so that the radiologist understand the rationale behind how those impressions were generated by the machine learning algorithm. So with this problem statement that when given a radiology finding, algorithm need to generate impression, we explore several summarization algorithms, because in summarization task there's a source text and then the target text. The model generates the target text using sophisticated neural networks or other traditional method, and generates the summary of the target text. So let me share some background on summarization. Basically, there are two types of summarization: extractive summarization and abstractive summarization. In extractive summarization, as you can see in this figure, a model just selects some of the salient sentences in the finding and present it as the impression. Basically, the sentences that are there in the findings are repeated in the impression, but only those that are salient, that model finds are salient. But the challenge or the drawback of such system is that several takes or portion of takes or phrases, such that in this case, phrases like there is, there, these likely, these things are repetition or not so precise information that the physician want to spend time looking into. They need to, um, they have very less time, and had to um, have they have to basically fetch right information in a very short time. In abstractive summarization, there is several tasks involved, and tasks like finding the topics within the findings, and then eventually generating the sentence from the scratch. They don't take any sentences out of the original finding. Even to make a concise summary, they often this system often introduce new word that concisely uh, presents the information that are there in the finding. As you see in this example, there is no repetition of the phrases like there is this and other stuff. A typical radiologist would write an impression in an abstractive manner. So we look into several abstractive approach and state of abstractive summarization, state of art abstractive summarization model. One thing that these abstractive and extractive summarization require is a lot of human level annotation, such that the model learns to perform uh, model learns to perform the task like a human does. So that is one of the challenge, and the latest state of art method are usually single step end to end model. For example, bought some apps. It has an encoder, bot base. Basically, encoder include self-supervised pre-trained bot encoder, and then adds another decoder which is trained from scratch using the finding and um, um, impression pairs. There are advanced form of such single step end-to-end model like two-step summarization, where this bot-based encoder is not only just trained on some summarization tasks like generating impression out of finding, but first it is fine-tuned to extraction task. Here extraction task is to take the source text and find out the salient sentence out of it. And then this fine-tuned encoder is then plugged into encoder decoder setup, and then then the summarization task is model is asked to do the summarization task. Lately, there are also two-step summarization, which has both extractor and abstractor in there. So, encoder decoder model that just does the extraction part, selects the sentences out of the findings, and then there is abstractor, another encoder decoder model that takes the extracted sentences out of the extractor and then rewrites it as an abstractive summary. um, um, as you can see, there are two components that are trained separately. The state of art model, what they do is they combine those through reinforcement learning. Here, the extractor becomes the part of it becomes an agent, and abstractor becomes part of environment. Now, whenever extractor selects the sentence and sends it to the abstractor, it just check whether the extracted sentences were matching the impression sentences, and if it does, then it receives the reward, and then guides the agent to only select such kind of sentences. As you see, this is a typical, if there is only sentence extraction, it becomes a single agent activity for this two-step summarization process. But now we have a lot of possibility to explore the extractor part. One possibility is that we explore the hierarchical nature of the text, meaning that the word eventually constitutes the sentence, and sentences eventually constitute the finding. So what we do is we, in our novel or innovative way, we also bring in the word aspect into the two-step summarization process, and we explore this innovative model on radiology report and check and evaluate how it works. I'll share the results in the subsequent slides. Here I will present this extractor part, and I'll only focus on sentence extractor first. So here extractor, again, as you saw in the previous slide, contains encoder and decoder. The encoder is on the left, um, as you see in the here, and the decoder is on the right. So in the encoder part, there are two aspects. One is like a lot of words in a report, and those words eventually constitute sentence, and several sentences are there in the finding. So first we run a bidirectional LSTM on words in a report, and then we get the representation for it. And we have a convolutional neural network that takes the word embedding and then position embedding and uh, generates the intermediate sentence representation. This sentence representation is passed as an input to another bidirectional LSTM. This LSTM then generates the sentence representation. During decoding, as you see in the right, at each step, it aligns its hidden representation with all the sentence representation and obtains uh, uh, attention distribution. And this attention distribution is basically used to select one of the sentence out of the findings, and that is done at each step. And at the end it also has this dummy symbol, which if it is selected, that indicates that decoder is done with the selection of the sentences. And these salient sentences that the decoder selects eventually is passed into another encoder decoder setup, that is the abstractor. We train this sentence extractor to maximum likelihood training. What we do is we take these selected sentences and match with the salient sentences. These are the ground truth salient sentences that are given to the model, and if it manages to extract all those sentences, then the model is trained properly. Um, as I mentioned previously, our innovative approach of doing this or doing extraction processes, we explore the hierarchical nature. And to explore the hierarchical nature, we need to build this word extractor. What word extractor is for doing is it's basically extracting the keywords out of the uh, report. So as you know, if there is extraction of keywords, this certainly would be going to be more numerous than the number of salient sentences in the report findings. So we need to align these two extractors. To align that, we introduce the switch network. So at every step, uh, if a word extractor is extracting the keyword out of the report, the switch network signals the sentence extractor to pause its activity. So meaning it would not select any sentence out of the finding section of the report, and the word extractor keep extracting the keyword. When it finishes extracting all the keyword in a sentence, the switch network then indicates the sentence extractor that it managed to extract all the keyword, and the switch sentence extractor need to decide whether to select that sentence or not. So the hierarchical aspect here comes into play. For example, if there are several keywords in a sentence, the sentence extractor manages to extract that sentence. But if there is only few keyword in a sentence, the sentence extractor just skip extracting that sentence, and it signals the word extractor to move to the next sentence and continue the activity of selecting the keyword. Here, what we do, in addition to sending the signal through switch network, we also share the context vector, which was used to obtain the attention over the word and sentence distribution at each step. So the context vector is passed from one for the words to sentence extractor, and same is for the sentence extractor to the word extractor. This is similar to cross-sentence mechanism. Now we have this encoder-decoder network for extractor. What we do is to train it with abstractor as part of environment, like the traditional two-step summarization. We put the encoder-decoder abstractor as an environment, and as you see, the extractor becomes now agent. Everything that are in dash blue lines eventually contributes to the training of the multi-agent reinforcement learning. So here at each step, if a sentence extractor is active, selects the sentence, it must receive the reward. So yeah, it takes the selected sentence and pass into abstractor. Abstractor checks with the impression, and if it has a match, it receives the reward. So the extractor agent has a reward at every step. For word extractor, it also has a reward at every step. um, for word extractor, if a word selected word matches uh, the keyword in the finding sentences, then it receives a reward of 1, else it receives the reward of 0. So now these reward at each step, uh, we do a discounted reward, and then do a policy gradient over multi-agent, here sentence extractor and word extractor. For We use actor critic, and that helps reduce the variance, like in like in traditional single agent actor critic. Here, during our centralized learning, the critic is aware that only one of the uh, extractor is active at each step, meaning like one of the extractor is at pause and another is selecting the sentences. So since the other actor is on pause, it becomes like a single agent actor critic setup for training the critic. So therefore the variance part, uh, or the value function estimated by the critic eventually would be contributing like a critic for only one agent in our setup, and therefore the contribution of uh, the contribution of the value function from the critic in this policy gradient would eventually be 0, and then variance is reduced. We call this system differentiable multi-agent actor critic. As I mentioned previously, there are two agents, which is like a multi-agent setup, and then we use actor critic for our learning of this multi-agent. Differentiable because we have this um, uh, uh, communicator, which basically communicates information from one agent to another. Here, the word extractor to sentence extractor to word extraction. So whenever there is a gradient component coming in, it goes through this communicator channel, and therefore the model is end-to-end trainable. Um, as I mentioned, the critic is basically only trained during the or it is only part of the during training, and since we are aware at any step only one agent is operating the value function contribution to this multi-agent actor critic setup, eventually uh, be like a single agent setup, and then the variance is reduced. uh, and yeah, the gradient contribution comes only from the agent. And additionally, we have this global reward, where um, the the selected sentences at the end and the selected keywords both are used and compared against the ground truth um, um, uh, impression, and then the heuristically obtained finding keywords, and then uh, we we use this hyperparameter to balance the contribution from the keyword, because the keywords are, as I mentioned, are not the ground golden label but obtained heuristically, but the impression are the golden label during training. So we have a lesser contribution coming from the keyword in global reward. So now let's move into the experiment that we performed, and for that we utilized a publicly available Mimic 3 database. It has several radiology reports. We clean it, and we eventually managed to have around 40,000 reports, of which 32,000 we use it for training, and 4,000 for validation, and 2,000 for testing. And as you see on the right side, we have some statistic for the different number of sentences in finding an impression, the number of words in finding an impression. You see, in general, we have roughly around 11 words in a sentence in finding, and slightly lesser number of words, that is 8.5 in impression sentence. Total word in the report is roughly around 87 with a very high standard deviation of 65. Total number of words in report impression section is lesser than finding section, obviously, and we have roughly around 15 words in impression, um, uh, and with a very high standard deviation of almost 60. As I mentioned previously, we only have finding section and impression section. We don't have any training level of which of the sentences in the finding are salient sentences, and which of the words are salient words that the extractor needs to extract. So what we do is we heuristically obtain those labels. To first we use autophrase, a supervised way to find out the keywords out of reports. So we use autophrase, train it, and get the you apply it on the report and find out the keywords out of a report. And then we for finding the salient sentences, what we do is we take an impression sentence and to combine with all the finding sentences and compute a Russell, and out of these Russell for all the finding sentences, the one that has the maximum Russell score against the impression sentence is selected as the salient sentence for that impression sentence. We do this sequentially over the impression without replacement. So eventually, the only one of the finding sentence is paired with the impression sentence for this extraction training, extractor sentence extractor training. The As you see now, we have two types of indices. One is for keywords, another for sentences. We need to interleave such that the extractor training that I discussed or said previously can function. So to do interleaving, we follow a simple approach. If a finding sentence has a keyword, we put that sequence first, and then if that sentence is part of the salient sentence that we obtain by matching the impression with the finding sentence that I mentioned before. If it is as considered salient sentence, then we take that indices and put it in that sequence, and we go over next finding sentence, and we do that sequentially for all the finding sentences. In this, we have a one big sequence of interleaved indices, and we uh, to distinguish which type of indices that are there in this sequence, we use this binary indicator. So binary indicator basically tells if a indices that is there in this sequence is of type sentence or of word. And in this way, this binary indicator would be used eventually to train the switch network that I said in the previous slide. So word indices would be used to train word. If a indicator says it is word indices, and when an indicator says that this is a sentence indices, then the word extractor becomes goes to the pause state, and then sentence extractor use that indices to train it to check if it can extract the same sentence indices or not. We do this pre-training, and then eventually we use those pre-trained extractor as a part of the agent, multi-agent setup, and then we have this extractor which basically is trained just using the impression sentence and then the salient sentences, and then this abstractor become part of environment, and we do multi-agent reinforcement learning using our advanced differentiable multi-agent actor critic setup. Following are the results. You see, we use several state-of-art method as a basis LexRank is a graph-based extractive system which take each sentence as a potential candidate and aligns with other sentence and find do a lot of cosine similarity and find out the most similar sentences, cluster of sentences, and use it as a summary. Pointer generator is sequence to sequence model, which has a copy mechanism, and when pointer generation with coverage basically is same pointer sequence to sequence model with copy mechanism, but with this additional coverage that um, uh, that restricts the decoder to not repeat the token, which is one of the problem with sequence to sequence model. Then we have Jang et al.'s method, which basically is a pointer generator with coverage, but with additional features that are available to decoder that lets better uh, impression generation. It is basically experimented on radiology report summarization task. But some apps is a uh, one step end-to-end model. Here, encoder consists of just BERT, self-supervised trained BERT as the encoder, and then the decoder is trained from scratch. But some abstraction is a two-stage system. Here, the first stage, the BERT encoder is trained to not only select the right salient sentences, and once this is trained, it just becomes the part of the encoder. The fine-tuned model becomes a part of encoder, so it is more tuned to learn, or basically it already learned the extraction part, and it now the decoder can only focus on abstraction part. But to let you know, the decoder is trained from scratch like birds and apps. BART is another self-supervised pre-trained sequence-to-sequence encoder-decoder model. Here, both not only encoder like in BART some apps and extraction apps is pre-trained, but also decoder is pre-trained. This pre-training is done on general non-medical corpus. Sentence rewrite is a single agent multi-step baseline for our work. Here, the single agent basically is doing like sentence is like a sentence extractor in our case. So it just extract the sentence, and rewriter is basically an abstractor which becomes a part of environment and rewrites the selected sentences from the single agent extractor. Differentiable multi-agent actor DMAC is our novel methodology where we have two extractor, basically the word extractor influencing sentence extractor based on how many keyword it manages to extract out of a sentence and indicate the sentence extractor to select such kind of sentences. So and utilizes multi-agent uh, reinforcement learning for training. So as you see, um, the transformer-based bought some abstraction works pretty good compared to LSTM-based pointer generators, but it doesn't perform as good as sentence rewrite and DMAX setup because you have a very small training data, and you are training decoder, which is a several layer of transformer network to achieve or to generate the multi-sentence summary. BART suffer more than BART some apps because BART is it's a several layer of pre-trained encoder decoder um, uh, that was pre-trained for some different task and was asked to generate impression after finding, which is very different and much tougher for it, and therefore suffers quite a lot. Sentence rewrite is very competitive. It is just a single agent sentence extractor based on LSTM and another abstractor pre-trained separately and just combined together using a single agent reinforcement learning, and has a pretty good result. But as we mentioned, the hierarchical aspect lets the sentence extractor, in our case, differential multi-agent actor, to focus on the right sentences, and therefore we have more precision-oriented setup, and therefore we have higher precision and maintain the same amount of recall that single agent sentence rewrite has, and um, is currently set apart for mimic dataset. In addition to do a quantitative evaluation using rules metric, we also did some human evaluation. We asked to certified radiologists to qualify some of the radiology report. We selected 16 radiology report from our test samples, and we gave these radiologists findings and three different version, blinded version of summaries. One coming from differential multi-agent actor-critic demand, another from the baseline model, which is the single agent actor-critic sentence rewrite, and the third one is the ground truth summary that is written by the radiologist. We asked those two radiologists to rate those based on two measures. One is overall quality, another factual correctness and completeness. In factual correctness and completeness, we ask them not only to assess whether they manage uh, to see the core uh, diagnosis or findings being recognized, but also check if there are any adjectives that are there in the findings, and the model manages to compile those or not. So if there are any attribute like laterality or anatomy associated with some disease, whether those are correctly compiled or not, would eventually lead to better factual correctness or completeness, and therefore they should rate those kind of summary higher. So radiologists eventually rated these three different versions of summaries in a scale of 1 to 3, 1 being bad and 3 being good. And as you can see on the right side, uh, compared to baseline model, uh, differential multi-agent wins in many cases. And we also do inter-annotator agreement, where we find that in both overall quality and factual correctness, the annotator agrees quite significantly, and believes that the differential multi-agent actor critic produces better summaries. Compared to ground truth, the BC ground truth summaries win against differential multi-agent actor critic, but the inter-annotator agreement is not very significantly large. This signifies that the although most of the time ground truth is selected, but within a report it might happen that sometimes one of the radiologists prefer model DMAC summary than the ground truth. But in generally, the ground truth is preferred by the radiologist. Um, let's look into one example from the model. As you see, we have summaries or the impression generated from obtained from the mimic report. We have one from the our DMAX system and one from the single agent sentence rewrite system, which is the baseline. We see that there are three sentences that are relevant for this particular report that the radiologist find should be shared with the referring physician, and the MAC system also finds those sentences and rewrites those, and the count is as like the radiologist written summary, but the baseline system has many more than uh, the that are actually compiled or that the radiologist feel. So here they have the max selected four sentences, and baseline system selected four sentences and then rewrote those in as a summary. And we observed this over the entire test set that the baseline system tend to select more sentences and has a better recall, though it suffers from precision. And as we mentioned in the very beginning, that the radiologists prefer more precise summary and with some explainability. As in our case, we not only share the precise sentences that were selected and also the keyword that the model found are relevant. Therefore, it's more explainable and more precise, and we believe it is more preferred by radiologists. With that, I conclude today's presentation, and I would like to share my conclusion. Uh, we presented in this presentation, I said our novel two-step reinforcement learn-based text summarization model that has innovative extraction process with not only one extractor but two extractors. We train this multi-extractor two-step system using differentiable multi-agent actor critic, where the communication channel allows gradient to flow from one agent to another, therefore becomes end-to-end differentiable. We evaluate differentiable multi-agent actor critic on English radiology report, and we find both in terms of quantitative and qualitative evaluation, the multi-agent actor critic model produce a better summary and more explainable summary than any baseline system. With that, I thank you for your attention, and I'm ready to take questions.